Alright, today we're going to do Equilibria energetics and elements from January 2011. Okay, we start off with a rate question, and it's actually given me the rate equation and the concentrations that react together and the initial rate, and it wants me to calculate the rate constant and the units. So this shouldn't be too difficult. We can rearrange this equation. So K is going to equal the rate divided by the concentration of H2 times the concentration of NO squared. If we substitute in our values for that, we've got rate as being 3.6 times 10 to the minus 2. Concentration of H2 is 1.2 times 10 to the minus 2, and we times that by the concentration of NO, 6.0 times 10 to the minus 3. Remember that. Right, so that gives us 3.6 times 10 to the minus 2 divided by 4.32 times 10 to the minus 7. If you do that, you get it to be 8.3 times 10 to the 4. Like so. How about units? Well, units, we know that rate is in moles per decimeter cubed per second. Concentration is in moles per decimeter cubed. That is going to be cubed because that's the power 1, that's the power 2. That's going to cancel out with that. So I'll end up with it being moles to the minus 2, decimeter 6, seconds to the minus 1 for my units. Right, so it now wants me to calculate what happens to the initial rate if I make the following changes. So let's pop up the rate equation just to remind us. Rate is equal to K times the concentration of H2 and the concentration of NO squared. So if I double this, so if I change that to K, double that, NO squared, what's going to happen to the rate? Well, the rate's also going to be doubled because I just times that by 2. So it'll be times by 2. If I now change that and I halve the concentration of NO, a half squared is a quarter, and therefore it would go down by a quarter. And then finally, I increase the concentration of H2 by 2 and the concentration of NO by 2. What's going to happen? Oh no, sorry. If I increase that by 4 and that by 4, let's change that. So if it becomes K 4H2 and 4NO squared is going to be 4 times 4 squared. So 4 times 4 times 4 is 64. So it would go up by 64. Right, okay, so the chemist carrying out the reaction between hydrogen and nitrogen oxide at a higher pressure. What happens to the initial rate of reaction? Well, the rate, we know, is going to increase. We should know that from AS. Why is that? Because there are more, well, there's a higher concentration, so let's put a higher concentration, and therefore more collisions per second. Fascinating. What happens to the rate constant? It doesn't change. The rate constant will not change with pressure. Possible mechanism. The key thing for your mechanism, remember our rate equation is this, you must put as your first step what's in the rate equation. So I'm going to put H2 and 2NO. Why 2NO? Well, because it's squared up there, that means I've got 2 of those boys in there. What could that do? Well, I've got to get to the overall equation. If I have a look at the overall equation, it's 2H2 plus 2NO goes to N2 plus 2H2O. So I've got to get to that. Can I make a product that way? Well, yeah, I can. If I transfer one of those O's onto the H2, I could make water. What am I left with? I'm left with N2O. What else I've got? I haven't used this H2 here, because I've got two of them. H2s, I've got to get rid of that because that doesn't appear anywhere. N2O. What am I going to make? I've got to make another H2O, haven't I? And I've got to make N2 like so. And hopefully you can see these two cancel each other out. That plus that gives me this. That and that gives me my two H2Os, and that gives me my N2. Right, time to go on to some transition elements now. And I've got iron and platinum to look at. So first of all, the electronic configuration of an atom of iron. They give me the first one, so it's going to be 3s2, 3p6, 3d6, 4s2. An ion of iron 2 plus, I'm going to lose those two electrons. Remember, they go from the 4s first, so I'm left with that. One property, other than its ability to form complex ions, it forms coloured compounds, which you know they're also catalysts. You know, iron is catalyst. Right, aqueous iron 2 sulfate takes part in redox reactions. Show using oxidation numbers that both oxidation and reduction have taken place. So we've got to work out oxidation numbers. You need to remember sulfate is SO4 2 minus. I've got one of those, so iron here is plus 2. Sodium is going to be plus 1. So if sodium is plus 1, that iron there is Cr2O7 2 minus, because I've got two sodium pluses. If that's the case, each oxygen is minus 2. And I've got 7 of them, which gives me minus 14. So minus 14 plus whatever two chromiums are has to add up to minus 2, which is the charge on the iron. So let's just work this through. 2 chromiums is going to equal plus 12. So chromium is plus 6. So each chromium is plus 6. Iron here, the iron here, so the sulfate, remember, is SO4 2 minus. I've got 3 of them, so the iron must be plus 3, because 3 times minus 2 is minus 6, 2 times 3 is plus 6. Chromium here, sulfate again, SO4 2 minus, I've got 3 of them. So each chromium must be plus 3. So therefore, Fe has been oxidised from plus 2 to plus 3, whereas chromium has been reduced from plus 6 to plus 3. Okay, they've now given us a ligand exchange reaction, and they want me to write K stab for this. Remember, you do not put water in K stab because they're all in aqueous solution. Water is in excess. So K stab for this. Now this is where you have to be quite careful. So I've got FeNH3 6 2 plus aqueous. And it's the concentration of that, so you need to put that in square bracket. So it goes a bit square bracket mad. On the bottom, I'm going to have FeH2O 6 2 plus aqueous, and again that always goes in square brackets as well. And slightly easier is going to be NH3 aqueous. You just need to remember that's the power 6 because you've got 6 of them there. Okay, that looks okay. We're now going to go on. Hemoglobin is a complex of iron 2. how do ligand substitutions react, allow hemoglobin to transport oxygen? So the key thing is the O2 molecules bond to the Fe2 plus ion in hemoglobin, and when required, so when the oxygen concentration in the body is lower, O2 is released. Okay, the final one. In the presence of carbon monoxide, less oxygen is transported. In terms of stability constant, suggests why. So, we can say the carbon monoxide complex must have a higher stability constant. It must be more stable. And because of that, that means that the CO molecule forms a stronger dative covalent bond to Fe2 plus than the O2 molecule does. Right, platin, which you would have heard about. One is used in medicine. It's a neutral complex. Why is it neutral? Well, it's because platinum has got a charge of +2, and I've got 2 times chloride ions, which gives me -2, and therefore they cancel each other out. Draw the diagrams of the stereo isomers. Well, okay, we're going to have platinum, and we could have the NH3s, NH3s, Cls, and Cls all trans to each other. Or you could have platinum with them cis to each other, like so. Describe its bonding. The ligand donates a pair of electrons, so ligand donates a pair of electrons to Pt2 plus to form a dative covalent bond, like so. And then the final one, describe the action of platin in the treatment of cancer patients. The platin binds the DNA of the cancer cells and it stops them replicating and therefore stops the growth of cancer cells. Right, so we've got an interesting one here. They want me to draw the structure of cyclobutane dicarboxylate ion. So cyclobutane is going to have 4 carbons in a ring. Notice you've got 2 carboxylate ions and they're on the same carbon. So it's going to look like that. You may just want to just make that a little bit clearer that they are carboxylate groups for the next one, like so. We now need to draw carboplatin. Okay, so if I start off like so, that is going to bond to these 2 oxygens here, and then let's work back. Like so. So that is bonded to the platin. That says similar as platin, it replaces the chloride ion, so I've still got the ammonia ions like so.